1984. 1984, maybe January or December. Is it possible that I can be able to have my analysis for that? And is it also possible for me to be able to get the deforestation rate, apart from kind of predicting and knowing maybe in the near future or this particular year how the deforestation will look like? Is it also possible for me to know the rate at which the deforestation rate, at the rate at which we're having deforestation, so that we can be able to even inform our partners or decision makers and be able to have mitigation measures that can be able to improve the forest status in our countries. Otherwise, this is a very impressive presentation, and I'm very impressed to listen to you, John.
Great, thanks so much, James. Right, sounds like you have a really interesting background for this. Probably you should be giving some of this tutorial instead of me. Maybe next year you can give the tutorial. Okay, cool. So on your questions, now the specific dates. The data set we have here only goes back to 2000. There may be other data sets. It might be difficult to go very far back, because to do this analysis of every single location that was deforested, you know, to get this kind of map here required satellite data, and the further back you go, the fewer satellites there were in operation where we can get data for. But there may be some stuff you could search around. What I'd suggest is to follow the link here about this this data set here, the global forest change. So they've got it up to last year. I guess some point this year they'll, or maybe at the end of 2020 they'll update this to say what happened this year. But yeah, it's Landsat 8. So this does have limitations when you try to go back decades. That's more difficult. Deforestation rate, that's also interesting. Yeah, because they modeled this as like just a binary thing, which is a simplification. So they're just saying at every location, was it deforested, yes or no? Of course, in practice, some things might be deforested a little, you know, or it might be total deforestation, like completely clear-felled. I think what to do there, so the work that this team did could actually be recreated. So they train a classifier, and it might be possible to actually use their methodology, but adapt that methodology to actually do a rate instead of a binary prediction. So I think there's some literature there which could be which could be helpful.
Oh, cool. That's okay. And maybe also you can also kind of try to improve your work by also looking at the other the other things that causes deforestation, like I'd said before, settlement, population, and any other that really affect deforestation. In addition to roads, I don't think roads majorly affect deforestation, but I will think things to do in East Africa or in this your area of study. I guess the major things that causes deforestation, I think will be settlement and maybe agricultural activities in forested areas. So if you will maybe incorporate such things, I think your model will be so impressive and will be so accurate compared to just using roads.
Yeah, really interesting. Well, it sounds like you have a project ready to go. Then you could take this as a starting point, and I mean that sounds extremely interesting. Yeah, add in those extra layers. Try tuning the prediction to make the best use of those extra ones. Try validating on particular years and see how accurate you can make this. But you could probably make it pretty accurate, I would guess. I share your optimism there. I think if you have all of those factors, you probably could get quite precise. Another thing which is interesting about this is here's where this particular data is available, and it's for everywhere in the world. So I just used a particular area of East Africa, but you could do this continentally, you could do the whole world, or you could go very precise to like local areas, you know, if there was some particular place of interest. Comment from Albert, since they use Landsat, most of the images could have a lot of cloud cover, usually a big limitation. Absolutely right. Yeah, big issue with any type of satellite-based analysis is clouds, especially when you're in the tropical region and things get misty and cloudy. I think what they do, and maybe this is why they have one prediction per year and it's not on a finer timescale. I think what they have to do is take a year's data and find a cloud-free composite. So you choose something like the most recent observation, which was cloud-free, and you hope that everywhere you have at least one cloud-free image sometime in the year, which is usually true because Landsat has a revisit time of every 2 weeks or something. So you have 20 or 30 chances per year to get a cloud-free view. So hopefully you have at least one observation. But sometimes that's difficult. I mean, places which are really cloudy, like Equatorial Guinea, is quite difficult. It's tropical and covered in forest, and yeah, sometimes it's difficult to get a lot of data. That's an interesting limitation. Okay, so we shall, I think, move on now to the second example, a bit shorter. We've got 15 minutes left. Ernest mentions, can we recap a bit for the recording? I think we weren't recording the first bit. So what we've done so far is looked at an example of deforestation. We have used this very interesting forest cover data set. We have taken data from the year 2000 and where locations were deforested subsequently. We've built up a predictor using like a Gaussian convolution on the deforested areas to get like a measure of where there was deforestation happening nearby. We've done a similar thing with roads. We've also taken protected areas and we've combined them into a 2D classifier, which seems to kind of work okay, and has data which can be exported into like a QGIS view for practical purposes. And there's been a number of interesting suggestions from people about how that could be improved. Okay, now the shorter example I'm going to get into here is like, what if you have information which is spatial and you want to make a prediction again on a map about something that's going to happen or something that is happening, but this time you only have locations from one or two places. So this is more like where you have information which is from GPS or which is from sensors, where you can't really measure everywhere in the same way that you could with satellite. The example we're going to take here is something we used last year as well, which is locations of cassava plants and whether they have cassava brown streak disease So thanks to the team in Macquarie AI Lab for providing this data. Super useful. I've simplified the data quite a bit. So what we see here is just a longitude, a latitude, and whether there's cassava brown streak disease 0 or 1. And we're just going to take a few samples from this and first of all plot them on a map. So each of these samples have been sent in by a person somewhere in Uganda about a cassava plant. This is a super impressive project because now it's got this great coverage all over the country. So interesting. Lots and lots of work have gone in by the team to set up this system. So this is really interesting and unique data. What I've done is plotted I've plotted the negatives in blue and the positives in red, and again used my current favorite little library here, MPL Leaflet, to convert this into an interactive map, so we can kind of see where the points are. Okay, so there's some areas where people send in more data from. Maybe there's one particularly motivated and active surveyor here who's sending in lots of data points in an area which is mostly brown streak disease free, and there's some other points where we seem to have kind of clusters of disease. So you can maybe see already, looking at this, that there are some spatial patterns. And imagine our job here is to try to come up with a disease map of the whole country. Maybe we want to report back to the authorities dealing with these matters. What's going on across the country, and where do we think that the disease is most prevalent? So we can treat this as a 2D classification problem again. Actually, it could be regression or a classification. You could think of this regression-wise as like predicting a rate. So, as in at each location, if you take some number of cassava plants, like what proportion of them are infected, and those infection rates can often be a useful way to model these types of problems. So we've got data which is like the input is an X and a Y and a binary target variable here, although you could think of this as a continuous thing between 0 and 1 if we were to predict it. And the problem is to predict other longitudes and latitudes. Like we've got these points. Now what's happening in between? Like what do we think is going on there in the middle? So this is something that we get basically for free with any classifier. What we're going to do is set up a grid of points on which we will do the prediction. So what I've done is set up a grid, and I've just plotted with pluses here, the locations where those where they are. So what we're going to do is we're going to make a prediction at the point for every one of these pluses. We're going to try to predict the prevalence of cassava brown streak disease at each one of these, and then again we can map it, export, and all of that. Okay, so there's some stuff here which we just have to kind of set up this grid. And what we're going to do is start to train a model. And again, this is super simple. So you've noticed that all the modeling, all the fitting and prediction that we've done really isn't any different from the normal types of classification we have to do. It's really just input which has some kind of two-dimensional nature where we know that one means latitude and one means longitude. From the point of view of a classifier, this is just two-dimensional data, so it's quite easy to work with. Okay, so setting up the variables. This is pretty easy. We have a model here. I'm starting with a really simple model, logistic regression. So logistic regression just has one parameter for each of the input dimensions. So what we're saying is like some weight times the longitude plus some weight times the latitude plus an offset. So when we predict that, okay, maybe that's a bit too simple. Like this is a model with 3 parameters, so it can't really learn anything very useful. I guess the best it can do is say, well, it gets more brown streak disease gets more prevalent in the southwest direction. But we can actually, let me put I better actually run these cells as well. I think I didn't earlier. Okay, so we could try a slightly more interesting model here, where we let's say we predict there to be brown streak everywhere that the closest observation we had was. Okay, so this prediction here is saying, like, wherever the nearest observation, take the nearest cassava plant we have in our database and predict whatever that was. So that's something we can do. It gets a little bit better when if we choose a number of neighbors and then we can okay, well, yeah, something's happening. Any drawbacks of nearest neighbors? Can anyone think of anything that kind of goes wrong when you use nearest neighbors to do the prediction? I see we've got 4 minutes left, so I'll accelerate a bit. One thing that goes wrong with nearest neighbors is if you don't have data anywhere nearby, your model is still equally confident. Like here we've got there's one observation where there was a cassava plant which did have cassava brown streak disease at this point. Now, okay, maybe this is. I hope you can all see this. This might be super tiny on your screens, I guess. Okay, so we've got like 1 point here, which was diseased. Now you can actually travel like hundreds of kilometers away, and maybe you don't have any data anywhere in between, and you're equally confident at all points. Just because the nearest neighbor, might be here, you're testing over there, and the nearest one you've seen might be 200 kilometers away, but it's still the closest, so you predict, okay, yeah, it's CBSD. So the issue there is not having any measure of uncertainty, and in this type of problem, the whole thing is that you want to be able to say there's some points that we're confident about and some that we're not confident about. Looking back at the data, we can see we've got some places which are very thoroughly surveyed, some where we've got like a few samples, and some where we've really got no samples at all. So, you know, we want our model to have some way of saying, like, here we just don't know. We've not seen anything for hundreds of kilometers, so our predictions are much less confident in that case. Whereas over here, we can be pretty sure. We really know what's going on. So this is where all the stuff that Charles was talking about, which he summarized, that I've just kind of recapped here, comes in. So we maybe choose some length scale, and we'd say, like, if we have observations in a certain point, like how far do we have to travel before we are unsure what's going on? For this problem, it's maybe in, like, you know, tens of kilometers or something like that. We can set this length scale. This is in decimal degrees here. So we've got like a length scale of 0.5 is like about 55 kilometers or something like that. So you could think of that as like when you travel some tens of kilometers in this particular problem, that's where you start to become uncertain again. And you can make some predictions. And so that's what the predictions look like here. This is the same type of thing that Charles was talking about as an example. It's a 2D problem, so we're getting we're getting predictions for each point on the grid, which I showed you above. I've plotted this in a way which makes the marker smaller the less confident we are. Okay, so with this type of prediction, we have uncertainty. Uncertainty comes back to us in this this variance output. So we have a prediction and a kind of uncertainty measure. So just plotting like this, the smaller the marker is, that means the uncertainty was higher. So there's places where we're very certain, and the disease rate is quite low, and then there's other places where we're somewhat certain and the disease rate is higher. And again, you could export this to GIS and make the output for your reports and your communication with policymakers and all of that. Okay, I see we are at the end of the slot. If anyone has any questions, then maybe we've got a minute to answer that while we hand over. Otherwise, we will leave it there. Let's have a minute just in case anyone has any questions to type them in, and then I'll sign off.
You can also put up your hand, and we can just enable you to talk, and you can ask it live. Okay, you have a few seconds to ask. Running down. Come on.
Going.
Going.
Cool. Okay. All right. Well, I think time's up. So thanks everyone for your attention. Great to be watching virtual Data Science Africa.
Great. Thank you, John. Yeah, so again, we want to give John a virtual clap. Why isn't there a feature to clap in Zoom? Great talk, John. Thanks a lot. Okay. Yeah, so if, again, please, we encourage you to go through the notebooks, the collabs. If you get any question as you're going through it, you can post it to the chat. We can always, the panelists and the presenters are still around, and they can still answer the questions. You can just direct it at any person, any presenter. Yeah, but we encourage you to go through the notebooks. Okay, so yeah. So the next presentation will be about data for good by Alex Pompe from Facebook. So we'll allow people, 1 minute to stretch, get a cup of coffee, or smoke a cigarette, whatever you need to do, and then we'll resume with the presentation in about 1 minute. And if you need to talk, you can always just put up your hand. Okay, so hope everyone is back. So we're going to start the next presentation. So this one is a recorded presentation. And Alex is I think at this time, the time zone is bad for him, he's still sleeping. But if you post questions, any of the panelists can attempt to answer them. There are still 8 panelists here, in case you want to ask any question. Can people hear this presentation? Sorry, I understand people are not hearing the presentation, so just give us a minute to try and sort this out.
Facebook. And I'm sorry I can't be there in person. Data for Good at Facebook's job is to find data sets within Facebook that can be shared with humanitarian NGO and academic research partners to save lives while preserving user privacy. So it's a really unique position. We work on sharing quite a few different data sets, and you can learn about all of them on our website, dataforgood.fb.com. Today, I'm going to talk you through the methods we use to generate some of our publicly available data sets and talk you through the case studies of how these have proven useful in fighting COVID-19 pandemic spread across the globe.
What is this thing?
So Data for Good at Facebook has been around since 2016. We have 3 different product areas where we work. And the products are defined by the source of the data we use for each of them. Our Maps for Good product is our longest running. We've been working on this since 2016. And we generate these maps using location or geospatial data that users opt in to providing to us. We also have a Surveys for Good vertical, where the data comes from Facebook users who choose to complete a survey that they see in their newsfeed. And lastly, we have an Insights for Impact product that pulls data from public Facebook posts. And some of that has been quite useful for COVID-19 work. So we have a pretty large menu. This is maybe breakfast, lunch, and dinner. So let's look for Good team. I'm speaking to you today remotely from my home. It's around 3 a.m. my time, so I thought it might for me to record this presentation so I'd be much more alert and awake. So thank you so much for inviting me to speak at Data Science Africa. We've been contributing to this now for 2 years in a row, the Data for Good team at Facebook, and I'm sorry I can't be there in person. Data for Good at Facebook's job is to find data sets within Facebook that can be shared with humanitarian NGO and academic research partners to save lives while preserving user privacy. So it's a really unique position. We work on sharing quite a few different data sets, and you can learn about all of them on our website, dataforgood.fb.com. Today, I'm going to talk you through the methods we use to generate some of our publicly available data sets, and talk you through the case studies of how these have proven useful in fighting COVID-19 pandemic spread across the globe. So Data for Good at Facebook has been around since 2016. We have 3 different product areas where we work, and the products are defined by the source of the data we use for each of them. Our Maps for Good product is our longest running. We've been working on this since 2016. And we generate these maps using location or geospatial data that users opt in to providing to us. We also have a Surveys for Good vertical, where the data comes from Facebook users who choose to complete a survey that they see in their newsfeed. And lastly, we have an Insights for Impact product that pulls data from public Facebook posts, and some of that has been quite useful for COVID-19 work. So we have a pretty large menu. This is maybe breakfast, lunch, and dinner. So let's look at the different menu options for each of those meals. So if you're working on COVID-19 response or really anything, our publicly available data sets are released without license restrictions. We produce very accurate and detailed population density estimates, which I'll go into great detail in a little bit. We also generate different data sets like movement range and social connectedness index, which look at how Facebook users are moving or how their relative friendship probability scores between 2 areas are useful. And we also look for street maps when we look at high resolution satellite imagery. So again, all of these publicly available data sets are released on the UN's Humanitarian Data Exchange, Amazon AWS's open data sets. Some of them we put on GitHub where we're able to open source them fully. And if you want to find out more information or download some of them directly, you can go to dataforgood.fb.com as well. So I'll go into more detail about all of these in a little bit later in the talk. There's also controlled access data sets, which are derived from Facebook mobile app users' location data, those users that have opted into sharing that with us. These are available to vetted NGO and research partners, where we generate unique logins for you to access these through a website. If you're interested in requesting access to any of these data sets, you can reach out to us on dataforgood.fb.com. I won't be covering any of them today. We're going to focus on those publicly available data sets. But if any of these sound interesting to you, reach out to us through the website. On the Surveys for Good space, we're going to discuss in more detail our Future of Business survey and our COVID-19 symptoms survey and preventive health surveys. We release the country-level summaries of these survey data sets publicly, but more granular response-level versions of these data sets are available upon request, again, at our website or through the external research partner we've been working with for the surveys. So you can go to our website if you'd like to find out about those controlled access surveys, and I'll go into more details shortly about the publicly available country summaries. And then lastly, in Insights for Impact, we have publicly available CrowdTangle dashboards, which allow us to look at content related to COVID-19 in over 80 countries. I'll explain the methodology and how to access those a little bit later. And if any of the controlled access efforts that you see here sound interesting, again, reach out to us through our website. So now let's take a look at the methodology and some examples and case studies of how the publicly available data sets that I mentioned are being put to use for the COVID-19 pandemic response. We'll start with our high resolution settlement layer. These are 30-meter population density estimates that are available for pretty much the entire globe. And the way we make this is by training machine vision algorithms to look at a 1.7 petabyte image of the Earth's surface and train these algorithms to do the same thing that you would do if you were flying over the Earth. You look down and you say, oh, that's a building, or that's a road, or there's lights on if you were looking at the nighttime. And we do this to generate very accurate maps of where buildings are located and thus where people live, where roads are located, or where there's electricity to light places up at night. And we do this by breaking the world into 30-meter by 30-meter grid cells like you see here, and we train the algorithms at a regional level, because we know that the vegetation and the building density and building type structure are very different in, shown here, Great Britain versus Niger. And you can see the results of the algorithm. So here's a satellite image looking down at the Earth's surface of a rural village in northeastern Namibia. It's a population of around 500 people, mostly subsistence farmers. Down in the bottom here to the left of the road, there's a school that taught grades 8 through 12. And up here towards the top there's a small cluster of buildings, and that's a health clinic. And everything else in the structures are mostly made of traditional materials, and these are mostly agriculture-based livelihoods. So we break this image like we do for the rest of the Earth into 30-meter by 30-meter sections, and then we ask our algorithm, do you think you found buildings in that 30-meter by 30-meter section? So let's see how it performs. So all of the areas highlighted in purple are the places where the algorithm is quite certain that it sees a building. You can see it's doing a pretty good job. It's pretty accurate. It maybe missed a few buildings, but there's very few false positives. So the algorithm is very, very good at knowing where people don't live, where there are no buildings. And we can do this with a much larger set of images. Like I said, we purchased this for the entire Earth's surface, and Facebook has a lot of computational resources. So we can do that same process like we did for the Namibian village, but for the entire globe. So let's see how that looks. Here we've assigned a different color based on the density of the structures in place. And when we remove the base image, now we're left with the most accurate population density estimates available. We do this by distributing census data from Columbia University's CSIN group. They predict what the results of a census would be if it were to take place in 2020. And then we distribute those census counts instead of over an entire census block. We put the people only in those 30 meter by 30 meter tiles where we detected a building. And this is the resulting image you see. That means we get to bring forward any of the demographic breakouts that are available in the census. So we here are mapping Nigeria, but only with the view of people over the age of 60. And so you get a sense for how fine-grained these 30-meter estimates are. And of course, you can see how this would likely be very, very useful for COVID-19 response, where you would be working with this age group, which is most at risk and vulnerable to this particular disease. It's been made use of by many, many different researchers for a wide range of applications. Population density estimates really have a very wide range of public health applications, not just COVID-19. On the left, I've taken a comparison of different population density estimates that have been used for malaria response work on Bioko Island. And on the right, this is a group of German researchers who use these population density estimates to predict how COVID-19 might spread in rural Germany based on different pathogen models. So it becomes very useful since diseases spread where people tend to live. They don't just cross big gaps of places of empty space. So these population density estimates are very, very useful for COVID-19 response. And all of the case studies shown here and throughout the presentation, you can read the full research papers that I'm drawing from on our website. We have them featured in the impact section of dataforgood.fb.com. So this was also, these data sets were used for the Ebola response in Eastern DRC, where researchers and NGOs had a very basic question that needed to be answered is, where do people live? If you're going to be delivering medicine or health supplies, you want to know, should I send 500 to village A? Should I send 1,000 to village B? To make those estimates, you just need a simple estimate of where people live. And so here we zoom in and we use the high resolution settlement layer for that area of Eastern DRC that was affected by the Ebola crisis. You can see that much of the area is uninhabited. There's sections of road where people are clustered around, and then there's villages at various places. But as a whole, it's a very sparsely populated area. So having accurate estimates of how many supplies to bring to a given place is very, very important. And since this data is made available publicly with no license restrictions, you can download it on the UN's Humanitarian Data Exchange. It was used in a variety of different open source applications. Here's one developed by a university in the United States, Ohio State University, where they added our population density estimates to data where health facilities are located, where border crossings were located, where vaccinations were being distributed, to produce a crisis map that was used quite extensively. Next, I'll talk about our movement range data sets. So when COVID-19 started, Facebook, as well as several other tech companies, began releasing these data sets that showed generally, are people moving around more or less compared to before the pandemic? And as governments put in place more social distancing measures, these became really important ways to measure the effect that these policies were having on reducing overall human mobility in the hopes of slowing down the spread of the virus. So the data looks like this for California. Pretty much everyone has been seeing these kinds of curves all over the news and in newspapers lately. We want to know, at what point did lockdown measures go into place and how much did overall mobility reduce? In this instance, we define mobility by looking at the number of 0.6 kilometer square tiles that a user visited in a given day. So before the crisis, I maybe lived in San Francisco and I traveled to Menlo Park every day to work at Facebook, and I maybe crossed 25 of those tiles. But now I'm working from home, and so I'm only present in maybe 1 or 2 of those tiles in a given day. That reduction from 25 to 2, we average across all the Facebook users in the county, and we provide that measure here, and we can compare the trends over time. They're updated every 24 hours. We also provide a metric, which is the percentage of Facebook users which we see present in only a single 0.6 kilometer square tile in a given 24-hour period. We call this the staying put percentage. So what percentage of Facebook users are staying present in just one tile? And you can see here a time lapse of Europe using our data. And you see Italy, France, Spain, they're all freezing. More users are staying in just a single tile. And now gradually over time, it's beginning to thaw. The movement rate is going back towards normal, and as social distancing measures began to relax in this part of the globe. And you can see, like in the southeast with Turkey, that there's many gaps in the data set. Whenever we don't have enough users to provide adequate privacy protections, we don't surface the data. So there must be a minimum threshold of users in a given space, otherwise we won't make the data available. We also, if you're interested in this space, we use a technique called differential privacy noise added to these data sets to make sure that there is a minimal amount of re-identification risk for an individual user. So when we take that average, the number of tiles visited by a single user, we add a random number to that total before we surface the data. The amount of noise that we add to this data set is specifically chosen so that it is equivalent to one user's maximum contribution to the overall aggregate within the data set. And in this way, we can ensure that it's impossible to re-identify an additional user, or it's materially probabilistically zero, be able to re-identify a single user, regardless of additional data sets that you might have in the future to try and do so. And so we published a paper on the Facebook research blog that goes into great more detail around this differential privacy approach so that you're able to transparently audit and determine the re-identification risk in the data set through a differential privacy framework. Next, I'll talk about our social connectedness index. This is a very interesting data set where we look at the entire world, all the Facebook users we have, and we break the world, let's say, into counties. So in San Francisco County and every other county on Earth. So which 2 counties have the most total number of Facebook friendship ties between users in those places? So maybe it's San Francisco County and San Mateo County. They have the most Facebook user friendships between them of any 2 places on Earth. They get a score of 1 billion. And then we take the 2 counties that have the lowest number of Facebook friends between them, and we give them a score of 1. And then we fill in all the values for all other counties on Earth between that 1 and 1 billion score. And that gives you, for any 2 counties on Earth, you get a single number, which is essentially the relative likelihood of friendship ties on Facebook. And so this provides a social connectedness score between different spaces. Here you're seeing the link, the more blue, the stronger the tie between aggregate friendship counts between San Francisco County and the rest of the world. And this has been proven to be very, very useful for COVID-19 response. So the virus has been proven to not just travel according to distance. It's shown here, these logarithmic curves, the level of social connectedness between Westchester County, which was one of the first counties in the United States that had a surge in COVID-19 cases. Additional cases were found in counties that had stronger social connectedness scores to that place, with a quite strong correlation. And so this social connectedness covariate is very, very useful for epidemiological forecasts who are trying to predict where the disease might spread based on current case counts. It's also been proven to be an indication of how people's behavior might be correlated. So different states in the United States, based on research by MIT, have followed similar behavioral norms of people when it comes to the spread of COVID-19, based on the likelihood of social connectedness as a measure of like social cohesion between places. So California and New York, people tend to demonstrate very similar behaviors, much so, more so than like New York and Arizona, which have a very weak social connectedness score. So this, the nature of social relationships in influencing people's behavior has been studied and proven, and has been very useful then for understanding how policies might translate from one area to another, and how likely that might be. So I mentioned before that we trained machine vision algorithms to look at the Earth's surface in satellite imagery layers and detect buildings, but we also can train those same or similar algorithms to look for roads or streets. And so we do that, shown here in this animation. We scan the Earth's surface for roads, and then we make a prediction to what type of road it is based on its properties to fit into the OpenStreetMaps model. OpenStreetMaps, if you're not familiar with it, it's like Wikipedia, but for maps, for roads. And so we predict where we think we have found roads that aren't present on OpenStreetMaps. And here you can see our algorithm doing so. We found close to 300,000 kilometers of roads that weren't mapped on OSM in Thailand. And we've done this for the entire Earth's surface for every single country. And we make those resulting predictions available on GitHub. We then work with the team at Humanitarian OpenStreetMaps, a really wonderful NGO. They work on validating our predictions using people. And if the road predictions we make are validated, then they get added to OpenStreetMaps. So that validation is currently taking place. But if you'd like to look at our estimates, you can find those on GitHub. And lastly, we look at the night, we look at the same satellite imagery layers at nighttime. And by looking at which parts of the world light up, and then using the street data and the topology of the terrain, we make an estimate of where the power lines, the electrical infrastructure grid, was built in order to electrify those areas. We did this in collaboration with World Bank. We've since open sourced our predictions and our algorithm, and they are now running the program. It's called their Global Electrification Program. So we've paused our development on it. But if you're interested in working on electrification projects or modifying our algorithm, you can find those on GitHub as well, or you can collaborate with World Bank, who uses this to make their estimates of how much funding will be required to bring electricity to the world's population to meet the global sustainable development goals by 2030. Now let's switch gears and go over to our surveys for good side of the product area. So like I mentioned, we can deploy surveys to the Facebook app, and people will get a request to complete a survey in their newsfeed. The surveys can be at most around like 35 questions long. And we have two different surveys that I'll cover today that have really been proven useful for the COVID-19 pandemic response. So the Future of Business survey is one that we have built in collaboration with the World Bank and OECD. So every month we have this survey go out to over 100 countries, and we ask around 35 questions related to economic livelihood to all of the SME page owners on Facebook. And we get data back from many, many thousands of respondents, and we get data for over 100 countries now. Since COVID-19 started, we've changed this survey. It used to run twice a year, and now we run it every single month. And we ask specifically around the economic hardships. Have they had to let staff go? Have they lost profit as a result of COVID-19? So this is very, very useful. World Bank has done very in-depth studies using this data to understand the differences in male-owned businesses in different sectors versus female-owned businesses, and specifically pointing out the gender imbalance in different economic sectors. For example, here, 96% of the automotive repair SMEs globally are male-owned. So there's different industries have a striking gender imbalance, and the men in the male-dominated sectors almost always tend to earn more than women in the female-concentrated sectors. So this is a really interesting way to look at the gender disaggregation of SME economic data that has really unparalleled reach by reaching so many different people on Facebook. We also, working with the University of Maryland and Carnegie Mellon University, have run a survey that people see in their newsfeed if they would like to answer questions related to COVID-19 symptoms. So are they feeling different symptoms associated with the flu or the coronavirus? We don't collect that data on Facebook. We refer people to answer that survey on our partners' websites. So we don't receive any of that data. This is what the survey prompt looks like. So it asks at the top if you'd like to take the survey and help researchers track COVID-19. It explains why the data is useful, who gets the data, and what data Facebook gets. They're typically around 3 to 5 minute surveys. We release the country level summaries of these survey results. Carnegie Mellon and University of Maryland do for all countries publicly. But if you would like the full response level data set, you can reach out to those academic research institutions, and you can find the information on how to do that on our Data for Good website if you'd like access to that data. And lastly, let's take a look at our Insights for Impact product family area. So this is the product which looks at public Facebook posts and tries to gather interesting insights from that. And so we have a tool called CrowdTangle. What CrowdTangle does is it tracks URLs and content across different social media platforms, Facebook, Instagram, Reddit, Twitter. And what it does is it basically allows you to search for what content, what images, which links are kind of going viral across those platforms. And we have produced CrowdTangle live display dashboards for over 80 countries. And so those are localized into the local language. And so it's really, if you want to think about it, it's like a very visual way to search social media and social media sites and see which content is trending right now. And so this is used for a variety of purposes and has been very, very useful for people trying to understand what type of content, what type of public opinion is surrounding COVID-19 in their particular country in the local language. So those are available. You can find the link to them, all 80 countries. You can find the links on our website at dataforgood.fb.com. So I wanted to thank you so much for viewing my presentation. Again, I'm very sorry that I can't be with you remotely or in real time. The time difference was just so difficult. But to recap, we covered today different publicly available data sets that come from Facebook's Data for Good program. Some of them are maps, some of them are surveys data, and some of them come from public posts on Facebook. And our goal with Data for Good is to empower the work of researchers and NGOs around the world to save lives while protecting privacy. So I'm sure that applies to many of you in the audience. You're all working very hard on the COVID-19 pandemic response, or you're building up the skills to do that in the future after you finish your schooling. So I hope these data sets can be useful for you and can be used to save lives wherever you're from. Thank you so much.
Okay, that was a recorded presentation. So Alex is not here with us now, but if there are any quick questions generally, people are free to ask, and we can ask one of the panelists to respond. You can just raise your hand if you want, or we'll give it another minute or so. If there is no one, then we'll